April 14th, a regular weekday. No announcements, no alarms, no reason to expect anything unusual. At 9:07 a.m., employees of a large IT company logged into their systems like they had done hundreds of times before. Coffee cups on desks, dashboards loading on monitors, routine meetings starting on schedule. Everything looked normal, until it didn't. At first, it was subtle. A few internal tools responded slower than usual. Someone blamed the network. Someone else refreshed the page. A support engineer noticed that a small batch of user data hadn't synced correctly overnight. Nothing critical, nothing urgent. By 10:30 a.m., the first real warning appeared. Customer-facing services began returning inconsistent results. Some users saw outdated information, others saw nothing at all. Error logs started to fill with messages that didn't match any known pattern. Requests were succeeding, but the data behind them was wrong. By noon, teams were pulled into emergency calls. Databases were technically online, yet records were missing. Backups didn't match production. Cache invalidation wasn't working as expected. Every subsystem claimed it was healthy, but together they told a different story. It was as if the system was slowly erasing itself, quietly, legally, following its own rules. Security teams were alerted. The first assumption was obvious: an attack. Was it ransomware? A breach? A compromised account? They checked everything. No suspicious logins, no privilege escalation, no foreign IPS, no malware signatures, no exfiltration traffic. Nothing. By mid-afternoon, the word attack was officially removed from the incident report. Then came the second assumption: sabotage. An insider, a disgruntled employee, a bad deployment pushed on purpose. But the deployment history was clean. Every commit was signed, every change approved, every pipeline green. At 4:48 p.m., someone finally asked the question no one wanted to ask. What if the system is doing exactly what we told it to do? Silence followed. Engineers began rolling back recent updates. The problem didn't go away. They reverted to older builds, still broken. They isolated services one by one, watching the same behavior repeat. Data entered the system correctly and vanished later, without errors, without warnings. At 7:12 p.m., a junior engineer noticed something strange. A function deep inside a dependency was behaving differently under very specific conditions. Not crashing, not failing, just making a decision that no one expected. That's when it became clear. This wasn't an attack. This wasn't sabotage. This wasn't even negligence. It was a bug, a single logical flaw, buried inside perfectly valid code, executing flawlessly, just incorrectly enough to bring an entire system to its knees. And the worst part? That piece of code didn't belong to the company. It wasn't written by an employee. It wasn't reviewed internally. It came from the outside, from a public repository, from a project no one remembered approving, from an author no one had ever met. By the time the company traced the origin of that code, the damage was already done. And somewhere else in the world, a teenager was going about his day, completely unaware that a single line he had written had just made him the most wanted person in IT. At the center of everything was someone no one was looking for. No office, no badge, no corporate email, no access to production systems. He was 17. No degree, no job title, no connections in the industry. He didn't work for a startup, a corporation, or a government agency. He had never signed an NDA. He had never even seen the inside of a real data center. Most days, he wrote code from his bedroom, a small desk, a laptop that overheated if he pushed it too hard. A second monitor he bought second-hand with money from freelance tasks and bug bounties. His world was a browser, a terminal window, and endless tabs of documentation. He wasn't trying to break anything. He wasn't chasing money, fame, or notoriety. There was no manifesto, no ideology, no plan. He wrote code for the same reason thousands of teenagers do: curiosity, to understand how systems work, to get better, to build something he could point to and say, "I made this." Most of his projects never went anywhere. Half-finished tools, small libraries, experiments that solved problems almost no one else cared about. He uploaded them to public repositories, wrote short descriptions, and moved on. No marketing, no announcements, no expectation that anyone important would ever notice. To him, it was practice. To the internet, it was free. Sometimes strangers starred his projects. Sometimes they opened issues. Occasionally, someone submitted a pull request. That was the extent of the feedback. He never checked download numbers. He never tracked usage. He assumed, reasonably, that his code was being used by a handful of hobbyists, if anyone at all. What he didn't know was how modern software really works. Large systems aren't written from scratch. They're assembled, layer by layer, dependency by dependency. 1,000 small pieces, written by people who will never meet, stitched together to form something massive. His code solved a narrow technical problem. Elegant, efficient, harmless. It worked exactly as intended, under normal conditions. And because it worked, it was trusted. Someone found it, then someone else. Then it was pulled into another project, and then another. At no point did anyone ask who he was. No one reached out. No one warned him. No one told him his code had crossed a line, from experiment to infrastructure. While engineers in a glass building relied on dashboards and guarantees, a teenager went to school, came home, and pushed commits without realizing that his lines of code were now running inside systems worth billions of dollars. He wasn't hiding. He wasn't anonymous. He just wasn't important enough to notice. Not yet. The project itself was small. Not a platform. Not a product. Not something anyone would build a company around. It was a utility. A narrow piece of code designed to solve a very specific problem. Reduce latency in a process that most developers accepted as good enough. He noticed a pattern others ignored, rewrote a small section of logic, and shaved milliseconds off execution time. On his machine, the improvement was obvious. Clean benchmarks, predictable gains. So he did what developers do. He published it. An open repository. A short README. A few lines explaining what the tool did and why it was faster. No bold claims. No promises. Just numbers and examples. It wasn't revolutionary, but it worked. At first, nothing happened. Then stars appeared. Then forks. Then issues from people he didn't know, using setups far more complex than his own. One comment stood out. Works great in production. He didn't think much of it. To him, production meant a small app, maybe a startup, maybe a side project. He assumed professionals would know what they were doing, that they would test, that they would read the code carefully. That assumption was his first mistake. Inside the IT company, pressure was constant. Systems had to be faster. Costs had to go down. Latency reports were scrutinized. Engineers were encouraged to optimize wherever possible. Someone, somewhere, was searching for a solution. They found his repository. The benchmarks looked good. The logic made sense at a glance. And most importantly, it was already being used by others. Social proof, without accountability. They didn't write the code themselves. They didn't fully understand it. They trusted it, because it worked. The utility was added as a dependency. Quietly. One line in a configuration file. No security review. No deep audit. No scenario testing beyond the obvious. Why would there be? It wasn't handling payments. It wasn't touching authentication. It wasn't supposed to be critical. Except it was. That small optimization was now part of a larger chain. It sat between components that assumed perfect behavior. It interacted with data flows the original author had never imagined. It was called millions of times a day. Under loads his laptop would never survive. And still, it worked. For weeks, everything looked better. Metrics improved. Dashboards turned green. Reports showed increased performance. Someone even mentioned the optimization in an internal meeting. No one mentioned his name. He had no idea his code was now inside a system that could not afford to be wrong. No idea that a shortcut he took, harmless in isolation, was about to meet conditions it was never designed to handle. The success felt invisible, but it was real, and it set everything else in motion. The problem wasn't obvious. There was no malicious code, no hidden access, no backdoor waiting to be triggered. The code did exactly what it was written to do. The mistake was smaller than that. It was a logical assumption. Deep inside the utility, there was a condition, a shortcut designed to improve performance. Under normal circumstances, it saved time by skipping unnecessary checks. The logic was clean. The math was correct. And in almost every situation, it behaved perfectly. Almost. The code assumed that a certain state would never persist beyond a narrow window. That assumption was reasonable in isolation, on a single machine, in a controlled environment, with predictable input. But production systems are none of those things. In the company's infrastructure, thousands of processes ran in parallel. Data arrived late, out of order, duplicated, retried. Caches were warm when they shouldn't have been. Queues backed up. Timeouts overlapped. Edge cases piled on top of other edge cases. And one day, all the wrong conditions aligned. Not because someone caused it, not because something failed, but because everything worked at scale. A rare sequence occurred. A delayed write, followed by a retry, followed by a cache hit that should have been impossible. The optimization kicked in. The shortcut fired. And instead of validating the state, the code made a decision. It wasn't dramatic. No crash, no exception, no alert. The function returned a value that looked valid. From that moment on, the system trusted a lie. That single incorrect result was cached, then reused, then propagated. Other services built on top of it, assuming the data was correct. New records were generated from corrupted assumptions. Old records were overwritten. The system wasn't breaking loudly. It was breaking silently. Each component followed the rules it had been given. Each service did its job. And together, they began to erase data. Not randomly, but consistently, methodically, according to flawed logic. Monitoring didn't catch it because nothing technically failed. Security didn't catch it because nothing was attacked. Testing didn't catch it because the scenario had never been simulated. By the time engineers noticed, the damage had already spread too far upstream to easily undo. Rolling back didn't help. Restarting didn't help. Replaying logs only reproduced the same outcome. The bug wasn't destroying the system. The system was destroying itself. All because of a single assumption written months earlier by someone who never imagined his code would run under these conditions. One mistake, perfectly legal, perfectly reasonable, and catastrophically wrong. Once the scope of the damage became impossible to ignore, the question changed. Not what happened. That was becoming clear. But who would answer for it? Incident calls multiplied. Internal reports grew longer and more careful. Every sentence was written with legal review in mind. The company needed a cause, a name, something external enough to contain the blast radius. Engineers traced the failure backward, service to service, cache to cache, decision to decision. Eventually, all paths converged on the same place. A dependency, an external library, code that didn't belong to them. That discovery changed everything. Suddenly, the narrative shifted. This was no longer an internal architectural flaw or a systemic oversight. This was third-party code. External responsibility, someone else's logic running inside their systems. The name of the repository appeared in logs, then in tickets, then in internal emails, then in messages forwarded to legal. Attached to it was a username, a profile, an email address, a teenager. At first it seemed absurd. Surely this was a mistake. Surely the author of a small open-source utility couldn't be connected to losses of this scale. But as the paperwork moved forward, his name stayed in the documents. It was easier that way. Accountability needs an anchor. Security teams began pulling records. Legal teams drafted questions. Compliance departments prepared timelines. His commits were copied into folders labeled evidence. Screenshots of his repository were archived. Every issue he had ever replied to was preserved. Without warning, things in his life started to change. His developer accounts were flagged, then temporarily restricted, then locked. An email provider requested verification. A hosting service asked questions. A platform demanded identity confirmation. Requests went out to internet service providers. IP histories were logged. Connection metadata was preserved for compliance reasons. None of this was dramatic. None of it was explained. At home, his parents received messages they didn't understand. Formal language, legal phrasing, references to systems, incidents, and potential liability. They tried to reach him through old contact details, through profile emails, through anything publicly available. Not because they expected cooperation, but because silence looked bad on paper. Meanwhile, inside the company, discussions continued. He wasn't accused of hacking, he wasn't accused of sabotage, but his code was now officially labeled as a contributing factor. That was enough. He didn't know any of this yet. He was still a teenager with a laptop, still answering comments on forums, still assuming that if something was wrong, someone would simply open an issue. The system was fixed, not quickly, but decisively. Engineers isolated the faulty logic, rewrote the dependency, and rebuilt the pipeline piece by piece. Data was restored where possible. What couldn't be recovered was quietly written off. Losses were categorized, reports finalized, and lessons summarized into internal documents no one outside the company would ever see. Within weeks, the dashboards turned green again. The company survived. From the outside, it looked like a rough quarter, a temporary disruption, a technical incident handled by capable professionals. There was no press conference, no public postmortem, no apology. The narrative was carefully contained. Markets moved on. Customers adapted. The story ended where it was supposed to. Inside the organization, responsibility dissolved into process. The failure became a case study, stripped of names and details, a reminder to review dependencies more carefully, a bullet point in a presentation about risk. And then it was over. No one reached out to the original author. No explanation, no closure, no acknowledgement. Around the same time, the teenager disappeared. His repositories went private, then vanished. His profiles stopped updating. Old projects were deleted. Contributions ended abruptly, as if someone had pulled the plug. There was no announcement, no goodbye post, just silence. Friends assumed he'd lost interest. Strangers assumed he'd moved on. The internet, as always, forgot. Officially, he was never blamed. No charges, no lawsuit, no formal accusation. On paper, he had done nothing wrong, but informally, the damage was done. Background checks became complicated. Applications went unanswered. Opportunities quietly evaporated. The same name that once appeared in open-source credits now triggered hesitation. Not because of guilt, but because of risk. Because no one wanted to be the next company explaining why they trusted him. He stopped writing code. Not out of anger, not out of protest, out of understanding. He had learned something most developers never do. In modern systems, intent doesn't matter. Scale does. And mistakes don't need to be illegal to be unforgivable. One bug, one assumption, one moment where the system worked exactly as designed. And that was enough.